Our first video of presentations. This is a way for you guys to stop, pause, speed up, rewind any notes and things you need clarification on when you're outside the classroom. So, nature of science is going to be our first unit in physics. We want to learn about how science works, and we're going to start that off talking about how we used to think science works. Let's look at the legacy of Socrates, Plato, and Aristotle. These three Greek philosophers were very influential. They were the quote unquote authorities in Western thought from about 500 BC to 1600 AD. Okay. They believed that somewhere out there, not here, there was some sort of ideal or perfect world. This just wasn't it. So, for example, we've got our tables in the classroom, and maybe they're a little wobbly or off center, but somewhere out there, there's some perfect version of the table, perfect, unblemished, uh, perfectly square, no wobbles, no cracks, no scratches. It's just not here in this world. And Aristotle was the one who pushed the idea of this perfect world or ideal, and he thought it was only accessible in your mind through thought and contemplation. So you could think about it, but never actually actualize it in the physical world here. Uh, Observations or things that you see, hear, uh, or even experimentation in this quote unquote dirty, nasty, imperfect world was pretty useless to the natural philosophers of ancient Greece because they couldn't understand a timeless truth or something that was always the same or always an ideal. So the science that we know of came from or evolved from this natural philosophy. The word natural philosophy means thinking about nature. And this started about in the year 1600, and mainly due to Galileo, Francis Bacon, and many others. And you'll hear this referred to as the scientific revolution. We credit Galileo as giving us the scientific method. And you'll see later on in the slides that there's a way of thinking for all scientific methods that follows roughly the same pattern. So from 1600 till now, like in the last 400 years, scientists have made incredible strides in their efforts to understand our universe, but there is still much to know. Scientific progress has brought about technological progress Galileo could never have imagined. So even with all we have now, there's still much to know. Currently, we have one of the greatest space telescopes, the James Webb Space Telescope. It's the best telescope we have for viewing images of deep space, even better than Hubble. And we're learning new things from that. In terms of nuclear reactions, there's one type of nuclear reaction called fusion that has always been like the Moby Dick of all scientists. They're always trying to catch it, and they're getting closer and closer today. So Galileo's credited with the scientific method. These scientific methods, I use plural, because the progress of science has not been linear. It has not been due to an adherence to a simple minded, step by step process, just like you learned in elementary school. So the elementary text would have you believe that the scientific method follows the same steps every time, but oftentimes it gets circular and has to go back to the drawing board, sort of like when we did the fortune teller fish lab. And we asked you at the end to think of another experiment or a way you might change your experiment. You don't always come to the conclusion, basically, at the end of every single experiment. And the reading from the textbook that I linked for you on Google Classroom, it tells us the success of science has more to do with an attitude common to science than a particular method. So the attitude is about inquiry, asking questions, experimentation, doing experiments, and humility before the facts. So it's okay if we're wrong. We can be humble and accept that. And we can always go back to the drawing board and do another experiment or look for more research or look for another someone else's experiment and do some readings on that. It just, bottom line is, it's okay if the process never ends. So let's keep in mind science itself, it's a huge and complex enterprise. There's no one in charge. There's no science council. There's no governing body. Just about any generalization about science and scientific methods is not going to be strictly true. So it's not like you can go to the United Nations and there's a science council, or there's no laws of science passed in the United States Congress, for example. And many people naively expect certainty and absolute truth from science, but science really doesn't have any of that. So, as we talk about science and science terminology, we want to use the same words and same language and have a common vocabulary. We need a common science vocabulary in order to communicate effectively with one another. So, those who are in science for a living that do research, when they publish their results, they do follow a similar format, much like people do when they do a lab report at school. Okay. So keep in mind that the scientific meaning of this world is often different than its everyday meaning. And I'm going to talk a little bit about that in a second here, talking about theories and laws. There's a lot of words in science like calories in physics. The calories on your food packaging is not the same measurement as calories in the physics lab. Calories in the physics lab are equal to 1,000 calories in the physics lab are equal to one of the calories on your packaging, for example. So here's a good place to start. Something that you notice is an observation. An observation isn't an experiment, it's something that you notice firsthand. It could be casual or even accidental. It could be formal. Someone could be observing turtles at a zoo to figure out what temperatures they like to breed at. So these formal observations could include experimental data. Not all observations are correct. Sometimes we make mistakes. We did our fortune telling fish lab, and maybe we had the fan interfering, or maybe we had our hand plus our partner's hand, or maybe we used their hand on the table. So sometimes the observations are telling us something, but they may be full of mistakes. So, how do I really know if something is verifiable? Well, with scientific observations, the first or primary way we have to tell if an observation is correct is to repeat it. And you can have other competent people repeat it. So your peers could repeat it, people in your class. So we want these observations to be repeatable. That's oftentimes when your teacher makes you do your experiment 3, 4, 5 different trials. You want to have a repeated result to verify that it's correct. So scientific observations must be repeatable. Anything that's non-repeatable is sort of the oddball out or the anecdotal evidence. So if I were a teacher and I said, well, I noticed it's really hot in here, but then the next day we had the fans going and it wasn't hot. Well, maybe that one day was the anecdote where the fans weren't on and I didn't notice that observation. That'd be sort of an anecdotal evidence. Now, an observation that your peers or many other competent observers agree is often called a fact. Scientific facts do not need to always be correct. Sometimes people make mistakes. So if we say fact or fiction in a different setting like English class, it means something different than in science class. Science is funny in the fact that it's willing to revise what is fact and what is fiction based on evidence, okay? So we say facts don't live forever or facts are not immortal. Further observations show that a fact could not be correct. You're going to have to replace the fact. This often happens when you have new technology available to make observations that cannot be made before. So sometimes a discovery comes along that helps us see things in a different light. I mentioned the James Webb Telescope. That's one thing that's happening right now is challenging people about the expansion of the universe. We've always thought that the universe is expanding, and we thought that it happens at a certain speed or rate. But now that has come into question based on these new observations from the telescope. Another example, when new technology or new resource becomes available, say, for example, dinosaurs, which I love, even though we're not doing biology, dinosaurs evolved into birds. And it's always been a mystery as to how dinosaurs and birds took off in their first flight. And was it from the ground or was it from the tree? Well, researchers did experiments with real birds, and they would put them on treadmills and make them run up on an incline and see if the bird would start flying. And so most scientists believe that birds took off from the ground originally. But new evidence came up from fossils found in China with tiny little microraptors, and it was shown that they started out gliding from tree to tree based on their bone structure. And that's cool, and it's okay. That doesn't mean the guy who was doing the treadmill birds is an idiot. He was trying to find an answer. So as long as you're willing to put in the work and find the answer, you're a scientist too. And we always say, aren't facts true? Okay. We assume that facts are absolutely true, but how could you know it? They're only going to be as true as you can prove it, or to our best ability to tell. That's all we can really say about them. I could say that the earth is flat. It doesn't look round. Well, from where I'm standing, it certainly doesn't look round until I do some other observation experiment. Perhaps I look at Earth from space, or perhaps I measure the difference in shadows from different locations. Maybe that implies a curvature. So facts are not always facts until we can verify them with observation and experimentation. A conclusion. Many times, if someone's giving a public speaking exercise, they have a conclusion or they say in conclusion. But our conclusion is really a decision based on the observations, our facts, or our experimental data. So all of our conclusions are basically from verifiable information, provable. What makes a law? Okay, this is different than the law, like you can't cross the street when the no walking signal is there. All right, the scientific law is a powerful summary of many facts. So once you have a bunch of these verifiable facts happening, and it happens over and over again, we can describe. Laws describe what happens, they don't explain why they happen. So there's a law of gravity, but there are different ideas on how gravity works. Okay, so laws can often be expressed very conveniently and concisely with a mathematical form. And physics and math are going to go hand in hand. They're like BFFs forever. It's sort of like learning the alphabet and grammar and then taking a writing class or a reading literature. It's the language of science. So the best part about that is it's verifiable and it quantifies or it counts and measures information. And we'll talk more about that in this unit. You guys did really good with hypothesis. Hypothesis is an educated guess about why something happens. And I like to take it farther. Remember, we changed it into a cause and effect or an if-then statement. So hypotheses have to be testable. There have to be observations that we can make and tell whether the hypothesis is correct or whether it's not correct. If you can't test it, it's called a speculation. Falsifiability. You might hear a hypothesis have sort of an anti-hypothesis called a null hypothesis, meaning an experimental test that could show if a hypothesis is wrong is actually much more useful than a test that can confirm only the hypothesis, right? So sometimes scientists are very strict in insisting that the hypothesis have a null hypothesis or a falsifiability to them. And, very famous scientists, you could look this up, said that they'd rather have been wrong multiple times than right just once. Because you could be right just once, but not know if you're right all the time. And we will get more into that in class when we start to look at experimental design. Okay, we spoke about laws. Let's talk about theories. Theories are sometimes used in the English language when you're talking to your friends. You commonly say, "Oh, well, she likes him because they played Roblox together," and that would be maybe just your theory. Maybe she likes him because he can dab. I don't know. That's my theory. That's not really a scientific theory, right? So as experimental evidence, observations, and data accumulate, we get more confident that our hypothesis is true. So a theory puts together or synthesizes a well-tested hypothesis. Like I said earlier, we know that gravity works. It consistently happens throughout the universe. It's a law, okay? And the theory could be, well, it happens because the objects are bending space and time, and we think that's why it works. Okay? So a theory is supposed to maybe explain how, and a law is supposed to explain what happens. Much, much different than the way we use in our common language when we talk to each other. So, like I said earlier, the scientific theories explain why the laws operate the way they do, and we often call them models. So in science class, we're going to do a lot of modeling, and the models that we currently have are revisable until we're absolutely certain that something has happened. We don't call it a law, and our theories always have to be quantifiable or highly mathematical in nature. So we need mathematical evidence, measurable results. So let's take a look at this quick comic strip. You've got the student on the left says facts are revisable data about the world. And the student on the right says, well, theories interpret facts. And this is a great summary of what we just spoke about. We've always misused the word theory. It's probably the most misused science term. Certainly by laymen, meaning people outside of the professional sciences, but even by people in science. We talked about scientific methods. Well, science is a process, okay? In science, you take evidence for the truth of any idea based on experimental observation. So data, results, experimentation, they give you evidence. Evidence leads to the truth. It's not like you have an idea of what the truth is and then you find the evidence later. So there's no science council, there's no tradition, there's no authority, there's no physics police. Sorry, so if you try to break the laws of physics, the physics police won't get you. Or anything else like that. You can't go to the United Nations and try to talk to the Science Council. It just doesn't exist. But peers are able to share their experiments, like publish their reports, and other scientists can reproduce that and see if they were right. So this process of testing facts, conclusions, laws, theories, experiments, observations, it never, ever, ever, ever ends. Ever. And that's okay. Science is a way of knowing. It's a process. Nothing, pretty much hardly anything is ever proven once and for all in science. So that's why when we were doing our fish lab, I was like, it's okay if you're wrong. It's just the process, right? And I think you guys were pretty good with that, and I appreciate you going along and trying your different hypotheses, and I hope you learned something from it. Maybe if you had a different tool to measure, like a different technology, you could have done the experiment a little differently. Or maybe the experiment could have helped you come up with something that you needed. So science discovers things about nature, about how nature works, but what we call technology, or these things that we come up with like inventions or applications of science, they use the specific discoveries to make, hopefully, practical structures and devices for society. And when I say hopefully practical, you could have something like nuclear power be helpful for the world and nuclear weapons be very harmful for the world. So to sum up, science and technology, science uses technology, and technology uses science. Science and technology are not the same, but they're related. So neither could exist for long without each other. I saw an interesting thing where, and I'll share this video with you, where they designed a road in another country. I forget where it is. I'm going to have to look it up. And when you're driving at the correct speed, the science told you how to create different sounds when it went over the bumps. And the technology was put into place to build the road that way. So the science of sound and the mathematical calculations on how to get the sounds were all put together into the technology of road making, to have people drive at the correct speed limit and get a fun prize out of it. So our wonderful physics students here are going to sum up. On the left, he says science is a way of knowing, and she says technology is a way of doing. So let's think of science as the knowledge or the process of finding the knowledge, and the technology as the application or the doing of the science. Okay, that's end of part 1.